Hey, good afternoon. Today we go to chapter 5, hierarchical models, and the reason why we've changed the order that we first went to this Monte Carlo and Markov chain Monte Carlo method STAN is that it's much easier to do the computation for hierarchical models using STAN. You'll notice when reading chapter 5 there is one section discussing how to do, even for very simple normal distribution hierarchical model and conjugate priors, it gets complicated. And so now when you are reading the chapter, you don't need to care about that specific computation part. So just focus on overall the concept of hierarchical model, exchangeability. It's useful to look at the H-schools example, even if the computation for that is much easier with STAN, but otherwise it's kind of the discusses these important topics in hierarchical models. Exchangeability is useful, but don't worry if you don't get the more deeper theoretical details on that. I will go some examples which illustrates kind of that why this useful concept when thinking about how to build hierarchical models. If you think about example where we have in this case, it's cardiovascular disease treatment effectiveness in different hospitals. And we could assume then that in different hospitals there's different people working there, different surgeons. There might be slightly different practices. There might be differences in how clean the operation rooms are and so on, which might affect then the survival probabilities. And then we could make a binomial model. You previously did already comparing two groups. You did two separate binomial models. But now if we have more than two, yes, we could still do separate models for each, but then we might also assume that there's something common between these hospitals. For example, if they are in the same country, we could assume that there's some similarity in the practices, recommended practices, and so also these treatment effectiveness. And so we could then build hierarchical model. So we could have also prior distribution describing then what would be the distribution of these treatment effects in different hospitals. Now, previously we had this kind of more flat models where we had the observations and then parameters for them, but now we have also then extra level that this tau is then also telling something about then on these thetas. And then now we, instead of fixing this, that what would be the population distribution for thetas, we want to infer that also from data. Terms, so this is familiar for you. We have observations and parameters. And so with the observation model, we have P, Y, a given theta, and the parameters have a prior P theta given tau. And then when we have priors which have unknown parameters, then they are called hyperparameters. Specific distinction when something in higher level is a hyperparameter, the the clear distinction would be that those parameters which are in the observation model, and on the other hand, which, when we're looking at the likelihood term, those which are directly affected by observations in the likelihood, they are parameters. And then, for example here, if we would know parameter values, then observations would not have any effect on hyperparameters. And only the information can flow to hyperparameters if we have also unknown parameters. So observations update what we know about parameters, and when we learn something about parameters, we can use that information to update what we know about hyperparameters. There are some cases where these are not as clearly defined, in a way that the people use sometimes sloppy language. And in machine learning, hyperparameters can mean also parameters which are related to algorithm, not just the model parameters, but which affect when you optimize something, for example, how this optimization is controlled. So there's sometimes danger of confusion. More terms. We use separate model term. Sometimes it's also called non-pooled, when we have separate model and there's no sharing of information between thetas. We have a joint model or pooled model, complete pooling, when we have just one parameter for all, so that all thetas are equal to one theta. And then in hierarchical model, we have many thetas, but there's something common between them, controlled within this hierarchical prior and prior parameters for hierarchical prior. The book has this example of rats, medicine testing, but now just looking at the control group. This type F344, it refers to certain strains of rats, so that they have common ancestors and they keep the genetic kind of diversity small, so that when they breed these and they provide them to different laboratories, then these type F344 rats are similar in different places. And of course, in a way, there might be otherwise difficulties, kind of the more variation, if you would use just any rat living in your local neighborhood. There's a lot of genetic diversity in rats living in different countries. In this case, it was just placebo, and then count how many get endometrial stromal polyps. And since there's a group of rats and counting, this is familiar binomial model example. There was 71 times this experiment has been made. These are probably in different laboratories. Sometimes it might be also that some of these laboratories have repeated some of the experiments, and then here are the results. And now then the question is what we can infer from these results. If we just pool all data together, this is what we would learn about theta. This is the probability that these rats get these tumors. If we instead make separate models, you can see there's, for each separate study, there's much more uncertainty, of course, because they are smaller studies. But we can see also there's variation between these studies. So it seems that there might be more variation between these studies than would be just explained that if the theta really would be something like this, and then we would repeat the experiments, we would not expect to see this much variation in the results which affect then these posterior results. On the other hand, we can see that they are not just all over the place. Most of these posteriors are clearly below 0.5, and overall there's reason to expect that there's something similar. Reasons why there can be these differences in laboratories, it's noticed that quite small things affect, like how often people go near the cage is already, the rats don't like humans coming to disturb their peace there. How much kind of how good the environment is. For these laboratory rats, at some point there was a lot of requests to improve their living conditions, that they should be able to, they should have more space and have toys to play and kind of these wheels to run around and so on. And when these changes were made, it was also noticed that many previous studies, if they were repeated, rats got less these tumors, they got less diseases, they lived longer, and there can be quite big changes sometimes depending on these conditions. And then even if they would be standardized, even if they are using the same strain and they should follow the same protocols, there can be changes in how the rats are treated or how often disturbed by just humans going near the cage. So we would like to know then how similar these experiments are and have a kind of something between, not completely independent studies and not completely pooled. And we can do this with this hierarchical model. In this case now, so we have there's this kind of graphical presentation of hierarchical models. The simple box around Yj tells that it's something which has been observed, so it's not unknown. Double box around Nj is that it was fixed by design in a way that there was first decided how many rats to have in the experiment. That's a double box, and then observing how many of those got the tumor, and just a single box. Unknowns are in circles, and at the lowest level we have there's a binomial model. Each Yj depending on number of rats in that study, Nj, and theta j, what is the probability of getting tumor in that specific study. In the previous slides I had theta j's going from theta 1, and then I had many theta j's there. Now this is kind of a space-saving way that we have plate. So this bigger box around all those things which have j kind of tell that this part of the graph is repeated and with the index j, and then j goes from 1 to some bigger value. Alpha and beta are also unknown, they are in circles, but they are outside of the box because these alpha and beta are then common for all theta j's. So we have a binomial model with unknown thetas, and for these thetas we have a beta prior with unknown alpha and beta we want to learn also. And then we can find out joint posterior. We can factorize this. So given alpha and beta, it's theta j are independent, and then we have a prior for alpha and beta. And then we would, of course, so this is actually missing also the product of likelihood terms for the posterior. So what would be good population prior then, what would be the hyperprior for alpha and beta? So alpha and beta for the binomial model, they could be also described as how many prior observations we have, non-tumors and tumors. And so they both affect the location and scale. You can read from PDA 3, page 110, the discussion of how to choose this kind of diffuse scale there. There might be also more informative ways to choose this, but this was not just something which is proper prior but diffuse. You can see the code for this example then in this demo 5.1. Here now we have then formed the joint posterior, and then we just show the marginal posterior for alpha and beta. You can see there, so there's a high dependency between alpha and beta. You can see that like when alpha is about 1, beta would be about 5. When alpha is about 3, beta would be about 15. So you can see there's the kind of the ratio 1 to 5, which is the most likely. There's a bit of uncertainty in this direction, and if you think about it, there was that if alpha and beta were considered as the prior observations, it means that when alpha and beta both are larger, it's narrower prior when we go in that direction, and then wider prior when we go to smaller alpha and beta. If we now draw from that joint posterior alpha and beta values, and then plot what kind of these beta priors would look like, you can see now this, so there's a bit of variation where the location is, but it is around somewhere a bit less than 1/5, which could be already approximately seen from the joints, and there's a bit of variation in the how wide these are. But this is what we've learned now of alpha and beta, and now if we integrate, so now these are posterior draws, but if we average over these, we get what is the kind of population distribution for if there would be new study made, what it would be our best guess for theta in a new study, and this reflects it. So we've learned something about possible thetas. It's very likely that in a new study we would observe also something less than 0.5, something larger than 0. Now in this case, this hierarchical prior was maybe kind of a bit arbitrary, or maybe because of the long tradition of using conjugate priors, it was chosen as beta prior, and that of course constrains a bit of this specific shape there, and there have been some people have also experimented with other priors and showing that there might be actually a bit of wider uncertainty closer to zero in this case. But this is anyway useful to illustrate the main point of these hierarchical models. Here I again plotted the results from separate models, but now only for a smaller set of studies so that it doesn't get so crowded. And one of them is then also plotted red, and you can then compare what is the difference when we have a hierarchical model. So instead of pooling them all together when we have fully pooled with just one parameter, which was very narrow, we have still a lot of uncertainty for the separate studies, but less uncertainty than with the separate models. So it is the benefit of the hierarchical model is that we are kind of borrowing information from similar studies and then reduce the uncertainty in each study. And then here you can also kind of see the comparison with the hierarchical model and what we learn about the population. In your exercise, there's this hierarchical normal model for factoring. So the book has this H-schools example, which I also explain soon, but which is bit of simplified, oversimplified example, and then this factory example then has more common hierarchical normal model. So the story here is that there's 6 machines in a factory, and then the one question is that is there possibly one or some of machines that are much worse than the others, or if we want to buy a new machine, is the quality of the manufacturer that good that we would predict that if we get a new machine, it is going to produce high enough quality that we want to buy a new one from that manufacturer. So each machine produces several products, and for each of the product, so we have some quality measurement y, ij. Now the machines are indexed by I, so we have a box around yij so that we have repeated measurements from one machine. Then each machine has its own average quality, theta j, and so we have average quality, and then we have also the variance parameter sigma squared, which are kind of telling that there's the average quality and there's the variation. And now we start with the common variation for all machines, and just the mean quality changes. And these are then affecting what would be the distribution of yij. But now we have a box around yij, so we observe those and then condition on those, and we want to learn about these unknown theta j's and sigma squared. And now we want to then have a hierarchical model, so we want to learn how similar these models are. And so it's not just the hierarchical model for reducing the uncertainty for each machine, it's also about learning how similar these machines are. In this case, we have the normal distribution model for these observations yij, and thetas have also then normal distribution with common parameters mu p, p as population, and sigma p. And then this can be extended, that we now assume also that each machine has its own unknown variability inequality. So there might be that some machine has much more variability than the others and have their own parameter. Now the prior for this sigma j is here inverse chi squared. This is also now, because of the tradition from conjugate priors, it doesn't need to be conjugate prior. Inverse chi squared prior is anyway a sensible prior also for positive values, but specific form comes from the history of conjugate priors. So other priors which are constrained to be on the positive scale could be also used. And with Stan, it's kind of, it doesn't matter whether they are conjugate or not. It's better to choose something which reflects your prior information. And so we have then also this population prior. Now they are then sigma 0 and mu 0 over there. In this factory example, we had from each machine several repeated observations. The H-schools example is also a hierarchical normal model, but there's small twist in the kind of the observation level. The background is that this is this scholastic aptitude test, very common in USA. They have been designed so that kind of the idea is that it should not be possible with very short time training to get high score. That they assume that it is really measuring years of school education, and then anyway schools have coaching courses, and also out of schools have coaching courses, and students are willing, or their parents are willing to pay for these coaching courses. The specific example is from years ago, and the idea was then to test that, are these coaching courses effective? So these SATs, they are standardized multiple choice tests. Then you get, like, the mean score is about 500, standard deviation about 100, and most of the scores are between then 200 and 800. And they are different topics, verbal, mathematics, and there's usually the students may also make also this pre-test. And so it's then possible to compare looking at the pre-test result, then there's a coaching, and then there's the actual SAT test. So in this case, the students had made these pre-tests in maths and verbal, and part of the students were coached. Now, instead of looking at these directly, how the score for each student changed, or what was the initial score and the afterward score, there was linear regression used to estimate the coaching effect for school J. This will simplify so that instead of looking at all the individuals, just look what is the average effect in each school. So there's the coaching effect estimated, but it has also the uncertainty estimate. And it's now assumed that in each school there were enough students that this coaching effect and its uncertainty specifically can be represented with normal distribution. So assuming now that yj are approximately normally distributed and with variances assumed to be known, since there is at least 30 students per school. And then instead of personal results, we have a group mean and variance. So we have for these 8 schools from age A to H, so there's the coaching effect, and then these, instead of variance, so now it's sigma j, these standard deviations. You can see that most of the effects are positive, but there's also a lot of uncertainty. And the question is then, okay, is this helping? Is the coaching helpful? So now we could think that we had first these Yij observations, but then it was summarized so that instead reporting directly now Y bar dot j, which is just average of these individual results. And then sigma j is, so the sigma squared is the, so the known variation, but then depending on how many students there are in each school, they can be different. And then we can still use this normal distribution model. So in a graphical form, the difference here is now that in addition of observing the y bar dot j, we also now observed the sigma j squared. And you can now compare this to the factory example, where we assumed sigma to be also unknown, either common to all machines or its machine having its own. In the same way, if we would have the individual data, we could then have common sigma for all schools or separate sigma for each school. But this is the simplified form. This is still the simplified form is enough to illustrate again this kind of that we are able to learn about similarity of the schools. So this is the separate models, and school A has been plotted with red line. We see there's a lot of uncertainty, and only for the school A it seems that there would be a bit higher probability that treatment effect is positive. But if we would then combine these, so there's the pooled model, there's more probability that it's positive than negative, but there's still some uncertainty that it might be also negative. And the hierarchical model. Now in this case, it seems that the schools are actually very similar. There's not enough information in individual schools saying that there would be much difference. So we have that they are quite similar, but also now in the hierarchical model there's a bit more uncertainty then that like some variation in the effects. It's useful to look at also the marginal posterior for tau, which was the scale of the population prior. We see that the most likely value is 0. And then again, it's not sensible to make the inference based on just the most likely value. We need to integrate over the uncertainty, and there's significant uncertainty, a lot of posterior mass away from 0. And when we integrate over this, we get that they are not exactly the same. This one is showing conditional mean with respect to tau, which shows also that kind of how this population prior affects. So with the 0, we would have all the conditional means to be the same, so completely pooled model. And with tau large enough, when the scale is large enough so that the prior is practically flat, where we have the likelihood information, then the conditional means go near to what would be the separate model result. But now we are integrating over the uncertainty about tau, and we get something which is compromise between completely pooled and completely independent models. And the nice thing is that then, depending on the data can tell what is the uncertainty about this population prior scale and how we automatically can find out how similar, how much we should pool, or how unsimilar they are not to pool that much. The conditional standard deviations illustrating that when we are pooling more, we are also shrinking each individual estimate more. And when we are pooling less, then we have more uncertainty for each individual. And more pooling, we are sharing more information between individuals, and less pooling, we are sharing less information between them. Sharing more information reduces uncertainty. This is something which is kind of the plots commonly used. This is radon example, which comes later discussed in one of the chapters, and showing that that when we have different number of observations in different groups, in this case this is different counties, and on the x-axis there's a sample size in county J. On left-hand side there's a separate model, and when the sample size in some county is small, there's larger uncertainty. These are now 50% intervals, and you can see that there's longer intervals for small sample size and shorter intervals for large sample size in county. When we add hierarchical model, it is learning the population prior, but it's also typical then that given the population prior, the results for these counties which had a lot of information are not changing much. There the likelihood was already narrow, so the prior has less effect. For the small county sizes, the likelihood was very narrow, and if the population prior is then learned to be narrower, it is shrinking these estimates towards the population mean. So it's also kind of in hierarchical models that more uncertainty we have about something, more likely we are saying that it's likely to be similar as what we've learned from the groups overall. Okay, questions?
So the thing that bothers me is that intuitively, in this specific problem, is that if you take the coaching and you do bad, it's probably not because the coaching was bad, it's because you didn't listen during the coaching, right? So we attribute, I mean, you don't say it out loud, but you kind of attribute causality coaching and causing negative results, which, according to common sense, this is not like a drug which may help you or not, or make it worse. Usually unless a teacher is teaching physics instead of math, when he prepared people for math, then you would expect either there's no effect or there's a positive effect. And since we have this sort of, wouldn't truncated normal make more sense in this example, because it sort of really clashes with my prior belief about how coaching would work.
Yeah, of course you could also assume that coaching should always have a positive effect and then use that kind of models. You could think that the coaching may have a negative effect in a way that if it makes the student, for example, rely that of course coaching helps and I don't need to otherwise, except in the coaching sessions, otherwise I don't need to do anything else.
Right.
The causality part is of course always difficult, but if we assume that the students were randomized, then there's a reason to assume that we can learn something about the causal effects. And of course, assuming that there were enough students, and in this case it also helped that we had the pre-SAT tests, so that we were looking at the change from the pre-SAT to actual test, and the coaching was between these. And of course there could be also other information helpful to improve causality assumptions. And this is kind of the effect being positive and negative. That's very good. Like the Bayer-Assau example, there we actually assumed that the effect should be always be bad. That this hazardous chemical cannot, if you increase the dosage, it cannot decrease the probability of death. So there we had specifically that it has to be just on one direction. In this case, I don't know whether negative coaching effect is sensible, but the conclusion specifically for this study would not change. And it would be sensible to do, for example, both models and compare how much it affects if you would assume that it has to be positive effect. And I've seen that this kind of studies also.
Now, in the previous slide, you had these three plots, right? So the first one says what's the probability of tau given the data. So if you have really small tau, which is like the standard deviation of the hyperdrive, then what we notice is the conditional means are basically like the pooled. And then as we increase tau, it's basically going towards the separate one. Now, if we have enough data, like if we have sufficient amount of data, is it always better to set the tau to something which is larger? Because then...
So we are learning tau from data, or the posterior distribution of tau from data. So now we don't know what is tau, and the top plot is showing the marginal posterior of tau. It is telling our uncertainty. So we have a lot of mass below 10, so it is, and also most of the mass is below 20. So you can see it's clearly favoring that it's not completely separate. There's a lot of mass shrinking a lot, but still there's so much uncertainty that it's not completely pooled model. And of course, if we would get more schools, then we would learn more about the similarity. Just so observing 8 schools is not much.